Since we're now talking about electrical potential energy, we need to make sure everybody's on the same page here and reminded of all the important basic ideas about energy, things that were first introduced back in 2201, thought about them a little bit when we thought about oscillations and energy and oscillations, but now we're thinking about them quite a bit more. So I wanted to take the time to go through some of the details. Energy is a property of a system, and a system is just some collection of masses that interact with each other. Interact means they're applying forces to each other and feeling forces from each other. Energy gets moved around within that system, and energy gets moved around between the system and its surroundings. Energy might come into the system from outside, energy might leave the system. Within the system, one thing might give some of its energy to another thing. In all cases, the process by which energy is moved from one thing to another is called work. Work happens anytime a moving object feels a force, or at least work can happen anytime a moving object feels a force. And the rule for calculating the numerical value of work in any situation: magnitude of force, magnitude of the displacement while the force is being felt while the object is moving, and then cosine of an angle. That angle is the angle between the displacement direction and the force direction, like I've illustrated here. The numerical value of work tells us exactly how much energy has been moved around. If it's a positive value, then the thing that was feeling that force gained that much energy, and if work has a negative value, then the thing that was feeling that force lost that much energy. Let's look at one example to think about how we use this equation. Just imagine you've got some big crate, and a rope is attached to it, and you're pulling the crate uphill. So here's initial location where the crate starts, here's final location where the crate ends, and a displacement vector always points straight from the start to the finish of some kind of motion. And while that crate is moving, it's feeling four forces. Of course, there's the gravitational force from the Earth, the weight pulling straight down, and then there's a pull uphill from the rope tension, and then this surface, this incline that the crate is sliding up, this surface produces a normal force. A normal force, remember, is always a push coming from a surface, and specifically it's a push in the perpendicular direction, perpendicular to the surface. So the surface is oriented like this, and then the normal force, the push from this surface, would be in a perpendicular direction like this. And then the surface is not perfectly smooth, so as the crate slides, it feels a force of kinetic friction. Whenever something slides across some surface that isn't perfectly smooth, there's always kinetic friction, and kinetic friction always points opposite to the direction of motion. The crate is moving uphill, so the kinetic friction force points downhill. And then what kind of work do we get from those four forces? First, work done by the tension force is just magnitude of the tension, magnitude of the displacement, cosine of the angle between the tension and the displacement, but the displacement points straight uphill, and so does the tension. They both point straight uphill. They both point in the same direction, so the angle between those two things is no angle at all. They are pointing in exactly the same direction, so the angle between those two vectors is 0 degrees of angle. Trigonometry tells us that the cosine of 0 is +1. So all we're left for the value of work done by the tension is just the magnitude of tension, magnitude of the displacement. That's all. And it's a positive number because these are magnitudes, sizes, absolute values, which are necessarily, by definition, positive. Positive work done by that tension force means that force is doing positive work. It's giving energy to the crate. Now, work done by the normal force, same deal. Magnitude of the normal force, magnitude of the displacement, cosine of the angle between displacement and force. Well, the displacement is along the incline. The normal force is perpendicular to the incline, so they're 90 degrees apart. Trigonometry tells us that the cosine of 90 degrees is 0. So even though this is a force acting on something that is moving, in this particular case, it does no work. It doesn't change the energy of the crate at all. Weight. Work done by the weight is just the magnitude of the weight, magnitude of the displacement, times cosine of the angle between the displacement, which is uphill, and the force direction, which is straight down. So the angle between uphill direction and straight down is this angle here that I call phi. So cosine of the angle between displacement and force, that turns out to be a negative number. Trigonometry tells us that for any angle greater than 90 degrees and less than 270 degrees, the cosine will always be negative. So we don't know the exact value of this angle. We don't have to. All we know is that it's an angle something greater than 90 and less than 270. So this is negative. The work done by the weight is negative work. It's taking away energy from the crate. And then finally, there's the work done by the friction force. Let's look at that, and I need to find an eraser first. Okay, here we are. Work done by the friction force, force of kinetic friction, is just the magnitude of that force, magnitude of the displacement, times cosine of the angle between the force and the displacement. Well, displacement is in the direction of motion of that crate, straight uphill. Kinetic friction points opposite to the direction of motion. So this points uphill, this points opposite to that. So those two vectors, the uphill displacement and the downhill kinetic friction, are 180 degrees apart, precisely opposite. And trigonometry tells us that the cosine of 180 degrees is -1. Negative work is done on the crate by the friction force. In other words, this much energy, whatever this number is, this much energy is taken away from the crate. Now, let's think in a little more detail about work. Let's think about work from a different perspective. let's imagine a system full of all kinds of objects, and imagine two of those objects interacting by means of some kind of force. So here's our system. Imagine everything in that area surrounded by that curve is in the system, and we'll think of just two things in the system, thing one and thing two, and they're interacting with each other, which means there's a force from thing one on thing two, and there's a force from thing two on thing one. And if one and two are moving while they're feeling those forces, then work is done. And let's say, turns out that the work done on thing one is positive. Which means, whatever the numerical value of that work is, thing one has gained that much energy. But energy doesn't just appear out of nowhere. That energy came from somewhere. And whenever there's work happening, it's always the case that the source of thing two, the source of the force that was doing this work, is also the source of the energy that the thing gains. So, in other words, energy is taken away from thing two and given to thing one. Energy being taken away from thing two because energy is taken away from thing two by means of work. This force on thing two does work, and it must be doing negative work because thing two gave up some of its energy, gave it to thing one. In other words, in this case, energy got moved around within the system, moved from thing one to thing two, but that energy that got moved around was moved around entirely inside the system, so that flow of energy didn't change the total energy of the system at all. One thing in the system had, let's say, 10 joules more than it used to because the other thing has 10 joules less than it used to. Well, that just means the total stayed the same. Or to say that in terms of algebra, change in the total energy of the system, E is our symbol for total energy of a system, is no change at all. Now let's look at a slightly different case. Thing one is still part of the system. Now thing two is something outside the system, but thing one and thing two are still interacting. In other words, there's still a force from thing one on thing two, and there's still a force from thing two on thing one. Right, forces like those will always be a Newton's third law pair. So, if we imagine that these things are moving while they're feeling those forces, then work is done by those forces. And now let's imagine, just like in the previous case, the work done on thing one by this force is again positive work. Which means thing one gained energy. That energy had to come from somewhere, and whenever work is moved around by means of energy, or whenever energy is moved around by means of work, the energy always comes from the thing that is the source of the force that does the work. So thing 2 lost energy. If it lost energy, it was because negative work was being done on thing 2. Negative work being done on a thing is how a thing loses energy. So again, there's a flow of energy from thing 1 to thing 2, but now that flow is a flow from outside the system, and the flow ends up inside the system. This energy that thing 1 now has was energy that previously was not a part of the system, which means that now, because of this kind of work being done, the system has gained energy. And the energy gain was the energy gain of thing 1, and the amount of energy that thing 1 gained is told to us by the numerical value of the work. So in this case, that increase in the system's energy, that positive change in the system's energy, comes from thing 1 having positive work done on it. Now let's look at a third example here. Again, thing 1 inside the system, thing 2 outside the system. And again, they're interacting with each other. So again, there's a force from thing 1 on thing 2, and a force from thing 2 on thing 1. Now let's imagine a slightly different situation. Let's say that now thing 1 is moving around differently than it did before. So as a result, this force from thing 2 on thing 1 does negative work on thing 1. That is, the work done by F2 on 1 takes this much energy away from thing 1, but that energy taken away from thing 1 doesn't just go poof, doesn't just disappear into nothingness. It must go somewhere. And it goes to thing 2. And if thing 2 gained energy, it must have gained energy by having positive work done on it, because work is the way things gain and lose energy. So in this case, we had a flow of energy from the system out of the system. The system lost some energy, lost this much energy. Right? The loss of energy for this system was entirely due to energy being taken away from thing 1. So in this case, the change in the system's energy is a negative change, and the amount by which the energy changed is just the amount by which thing 1's energy decreased. The amount of energy taken away from thing 1, which is numerically equal to the work done on thing 1, the negative work done on thing 1, which is a negative number in this case. So one thing we see here, whenever there are forces that come from outside the system, right, this force on something inside the system comes from outside the system. This force on something inside the system comes from outside the system, comes from thing 2, which is not part of the system. Whenever there's a force that comes from outside the system, we call that an external force. Whenever that force exists, and if that force does work, that will change the system's total energy. If that external force does positive work, it'll increase the system's total energy, and if that external force does negative work, it'll decrease the system's total energy. Or to say this in very, very general terms that apply to all situations, we can say this. Work done by external forces causes a system's energy to change. And in the first example, we saw that work was done by an internal force, that is, a force that is not external, a force that had for its source some piece of the system. In that case, work was done, but that just shuffled energy around entirely within the system. So we use this symbol plain old W with no subscripts, which means the net work done by external forces and if there is net work done by external forces, that's what changes a system's energy, just like in the second and third examples that I looked at here. So the net work done by all the external forces will be the thing that changes the system's energy. And it's only external forces doing work that change the system's energy. In the first example, we saw internal forces doing work that did not change the system's energy. So we might also want to say the work done by the net internal force is zero. As a matter of fact, always zero. Now, when we're talking about electrical systems, a system that is made up of two or more charged objects, we'll almost always be using a simple approximation in which our system is well isolated from any other things, isolated enough from any other things that other things don't apply forces to anything in the system. In other words, there are no, in our approximation, in our simple models, there are no external forces. And if there are no external forces, then clearly there is no work done by external forces. So most of the time, we will imagine no work done by external forces because we'll imagine a situation in which there are no external forces in the first place, which means the change in the system's energy is zero change. The system's energy stays constant. That's usually how we'll do it. And just about all the time, the system's total energy will simply be a sum of kinetic energy plus electrical potential energy. Every time we've thought about total energy previously, it had always involved some kinetic energy and some kind of potential energy. In this case, we're thinking just about electric potential energy. Now, as you saw in the reading, there's this thing called electrical potential. Sounds like electrical potential energy, but it's not the same thing. It's closely related, but it's not the same thing. The way it works is that if you've got some charges in some region of space, that region of space, as we've said before, is now filled with electric field, and that region of space now has electric potential at every point in that space. And if there is electric potential at some point, and then you go and move an electric charge to that point, now you have electric potential energy that you did not have before. And the rule goes like this: the electric potential energy is just the charge that you moved to that point X, let's say, times the electric potential for that point. You want to think of this potential as caused by other charges that were already there in the first place before Q came into the picture. And then when Q does come into the picture and starts interacting with those other charges that were already there, then you get electric potential energy that you did not have before. Usually that electrical potential energy happens because you had to do work to move this charge into that region of space, and by doing work you've given energy or maybe taken energy away, either one, and so as a result you got some potential energy that you did not have before. Now consider the change in energy. Anytime there is a change in energy of a system like this, it would be a combination of a change in kinetic energy and a change in electrical potential energy. But what did we just see? We're usually going to imagine a system that has constant total energy. So the change in total energy is zero. So change in kinetic plus change in electrical potential energy must always cancel out each other out. If there's a change in one, there has to be an equal and opposite change in the other to keep the total energy constant. Or you could write it this way. Just move one of these to the opposite side of the equation, and we have change in kinetic energy equals minus change in electrical potential energy. The two changes have the same magnitude but opposite sign. When one kind of energy increases, the other one has to decrease by the same amount. That's what this equation says. Now, combine this with this, and we get one more useful result. Let's think about, in a little more detail, about change in electrical potential energy. As you remember, change in anything is the final value minus the initial value, but we can think of final and initial potential energies this way. The final electrical potential energy is just charge times the final potential. In other words, we're imagining moving Q around, and then V final is the potential at the location where Q ends up, minus initial electrical potential energy, which is just Q times the initial value of potential. This is the value of potential at the location where Q started. Right? Q starts at a location where this is the potential. Q ends at a location where this is the potential. Now factor out the Q, and we have that simple relation between change in potential and change in potential energy. But because of this, right, the minus 1 times the change in potential energy is just the change in kinetic energy. Delta K equals minus change in potential energy. In other words, minus 1 times this. And that turns out to be a relationship that we'll end up using quite a bit.